Hi, everyone. My name is Carson Whitenauer, and I serve as the Executive Director for Uncommon Pursuit. And today we're going to be talking about a very interesting and critical question. Does the universe point to God? And it's a question that I think we all have when we get out and we look at the starry sky and we wonder, how did all of this get here? Did something come from nothing? Does this mean anything? Does this have any religious significance? These are the questions kids have, and thankfully, they're the questions adults have too. And I'm thrilled to be joined by Dr. Luke Barnes. He is a lecturer in physics at Western Sydney University. He works on cosmology, galaxy formation, and the fine-tuning of the universe for life. And I really enjoyed reading Luke's book, A Fortunate Universe. He's got another resource, The Cosmic Revolutionaries Handbook, both published by Cambridge University Press, and he did his Ph.D. at the University of Cambridge. And so, Dr. Barnes, I'm sorry you didn't have the privilege of studying at Oxford. I did a study abroad term there, but I'm willing to set that aside for today's event. Today, we're going to go for it. We're going to do a deep dive and get into some terminology that might take a little bit of explaining, but hopefully it'll be a clear and accessible conversation. And you will notice if you read the book that Dr. Barnes has a fantastic sense of humor. And so if all you get is the jokes, then I hope you feel well served today. So Dr. Barnes, I'm just curious if you would share with us what led you to become an astrophysicist.
Oh, okay. So, actually, I was always a bit of a science nerd growing up, but more of a dinosaur nerd than anything, knowing all the types of dinosaurs. But was always good at mathematics, and so as part of that, at the end of high school, the last couple of years, did physics at high school and realized, oh, you can actually use all this mathematics out in the real world. And then the more I studied it, the more I wanted to study it. So I actually did a first year at university of a surveying degree, but as part of that did first year physics because it was really an engineering degree, and then realized, oh no, this physics stuff, it really is the stuff that I want to do. So did a physics degree. As part of that, discovered that astrophysics is fantastic, really fascinating stuff. And then from there, started doing sort of little undergraduate research projects and an honours degree, and yeah, just kept sucking me in every step.
So as I read A Fortunate Universe, I was struck by some different points you and your co-author make about how interesting our universe is. The first one is that, hey, we're here. There's people who are interested. And it's interesting that there are observers to notice this universe. And I think maybe it's just arrogance or, naivete, but often I take our existence for granted. But it's actually pretty peculiar that there are observers who are fascinated by this universe. Another thing is whatever we get fascinated by, whether it's star formation or, the fundamental nuclear forces, everywhere we look in your book, there is incredible fine tuning. And it's very interesting how precisely this is measured and how specific and important it is that, hey, it be right in this extremely narrow value. So I think that's a very interesting thing about our universe. And then the other part of it that was super interesting is how these vast amounts of data and these cosmic explanations get reduced down to these very tiny, simple formulas. It's fascinating that E equals mc squared is an equation that describes fundamental realities in our universe, and it's so simple and elegant, but has so much power. And then another part of the fascination, and this is coming from looking at the James Webb Telescope and some of the images coming out of that, is it's so beautiful that the order is lovely and it's interesting to look at, and just it's mesmerizing imagery when we see what this universe is composed of. And I wondered if you could speak to that as an astrophysicist about the sense of curiosity and fascination and finding the universe interesting time and time again.
Yeah, so I mean, as you look around you, there's obviously complexity in the universe. There's obviously, I'm looking at a tree outside. There's obviously a lot going on there, and the amazing thing, sort of, on the other end of astronomy, on the smallest end of the universe, the deeper we look in there, into the structure of the cell and all those sorts of things, and just incredible complexity. The amazing thing is that the complexity doesn't go all the way down. That as you start to sort of break things down, if you take a part off the tree and you break it down, there's 92 chemical elements that's all made out of fundamentally, and then those elements are made out of three particles: proton, neutron, and electron, and protons and neutrons are made out of quarks. But that's another story. But fundamentally the tree is complicated, but the laws that follow is much less complicated than the tree. You've got to speak the right language, the language of mathematics. And it's still, if I showed you the equation, you wouldn't think it's that simple. But it's, much, much less complicated than a tree.
I want to get into some of those particulars from the biology of life to the formation of the universe with you. At one point, you write, in keeping with the running theme of this book, reality is slightly more complicated than our discussion. I appreciated the honesty of that this is more of a popular level book, and compared to the mathematical equations or the reams of data your supercomputers are processing, this is a little bit of Astrophysics 101 for us. But I wanted to just get it out there. What are some ways you see Christians or anyone interacting with this conversation about the fine-tuning of the cosmos and some of the basic errors and ways of talking about it that you just scratch your head and go, they have no idea what they're talking about?
Yeah, so chapter 7 of the book, which is just over my shoulder there, is dedicated to ways that that we've seen people interact with fine-tuning that we don't think are sort of the right answer. We think a lot of people see instantly there's something interesting going on here, that if you make small changes to the fundamental way our universe works, then you end up with a universe that can't support life or intelligence or anything like that. And so I should say my co-author Geraint is an atheist as well as an astrophysicist like me. He was my honour supervisor, amongst other things. They're my colleague. So we wrote that chapter together as well. So there's ways that a Christian and an atheist can look at fine-tuning and think, like, here's some wrong answers, and there's a lot of them in that chapter as we pull it apart. I think one of the most important ones is that it's not something just made up by Christians. This isn't just something religious people made up. The way it started was in the physics literature, and it was physicists like John Barrow, like Paul Davis, Brandon Carter, people doing their job as physicists, looking at the way the world is, looking at the way it depends on the numbers that it depends on, who just noticed this really odd thing. If you start to change these numbers, it all goes pear-shaped. So there is a vast scientific literature on this topic that is not just, it doesn't just exist in, Christian apologists, books.
I think that's helpful. And can you speak to that collaboration with Geraint, that this is something y'all have profound religious differences about, but there's a deep mutual respect, there's a friendship, there's an agreement on the scientific data. What do you hope, just by modeling that, you model a friendship and a collaboration in the book, and I think our world has become so divided and polarized. Do you see some lessons for us in that conversation?
I mean, it's entirely organic. It's not like I went out and thought, I should go. So the way it actually came about was when so I was his honours student at the University of Sydney. I then went and did a Ph.D. at Cambridge, which he also did, so he was very helpful in navigating me through that application process. I then had 2 years as a postdoc in Switzerland, but then got a job back at the University of Sydney working with Geraint and a bunch of other people. In the meantime, I'd done a whole bunch of research on this fine-tuning stuff, written a review paper, and a couple of people at the astronomers there at Sydney, there's quite a big department there, wanted to hear, to talk about it. So I gave a talk, Grant's in the audience, and so it was a nice sort of convergence of, we're working on stuff together anyway. I know about this field quite a bit, and he'd been thinking about writing a book. And not only that, he almost sort of had a contract to write one on something else, but then that fell through for various reasons, and so he thought, let's write a book about this. So, it all just sort of fell into place. The nice thing about this is you really can, because it's not sort of a Christian apologist conspiracy, because it's out there in the literature, because it's physics, we could just write 7 chapters together and agree on almost all of the physics, and then just, take one chapter at the end. Chapter 8 takes the form of a conversation. So we just chat about what the differences are, and then that's it. And so when we were promoting the book, we do sort of a double act. We gave a talk at the Royal Institution in London. That was great. We do half of the physics each, and then I do my perspective, he do his perspective, and then we just leave it at that.
I think that's. I'm glad that it's not. Y'all aren't trying to prove a point. It's just you truly respect each other, enjoy working together, and there's a real friendship there. And I hope that those kinds of conversations will multiply. So there's obviously 2 parts to your book, and so I think there's 2 parts to the discussion. And part 1 is just getting familiar with, is the universe fine-tuned? And clearly the answer here is yes, but getting into some of the details of that. And then the second question is the so what question. Does that mean that the universe points to God, or actually points to a multiverse, or fits best with naturalism? And so my understanding is that there are a lot of different ways to look at the fine-tuning. There's the stuff itself, there's how the stuff is connected, and there's where the stuff is connected. So the stuff is the fundamental particles, the bosons and the fermions, the up quark and the down quark and the electron. You've got the connections, or all the fundamental forces. You've got gravity and electromagnetism and the strong and weak nuclear forces. The where, you explain, that's the space and time, which was kind of mind-boggling. Okay, the where is space and time. It's pretty comprehensive. But there's an especial focus on how weird the Big Bang is. And then in all 3 of those areas, you're just marveling at all of the constants that have to be plugged in from observation to make these equations work out. And so that's a lot of different areas to find fine-tuning. And I'm wondering if you could share with us a few examples of the fine-tuning that you find particularly interesting.
Yeah, so actually that's a nice division. So in terms of the stuff, one of the most basic properties of the stuff is mass. So we're familiar with mass, things weigh a certain amount. So electron, for example, if you remember your picture from chemistry, there's the thing going around the outside of the atom, that's the electron. It has a certain mass. It's extremely small, but we can measure what that is. It's more complicated to do, but we can measure the mass of the up and the down quark that make up protons and neutrons, that make up nuclei and atoms and all, so on and so forth. So what we can ask is, what if these masses had been different? So what if the electron had been heavier? What if the up quark had been lighter? Now, you might think that what that's going to do is just make everything in the universe a little bit heavier or a little bit lighter. But actually, the reason why it matters is because at a fundamental level, when you get down to those different types of particle, they are involved in, various reactions that sort of convert them into each other, so to speak. Various nuclear reactions that are quite important to the way the universe pans out. The other reason why they're quite important is whatever the lightest particle is, whatever the lightest set of particles are, those are the ones that are the most stable. Because if you have because of there's that equation E equals mc squared. The heavier particles have energy there. So if there's a chance for them to undergo some sort of reaction or decay or something and transform into another particle, there's enough energy there for them to do it. Whereas when you're down to the lightest particle, there's nowhere for it to go. So there's all sorts of ways you can put quarks together to make heavy things, but if they then sort of start to decay and transform and you get down to a proton, then you're done. That's it. Your proton's your bottom, as far as we know, the sort of bottom floor. So it goes to, once you start changing these numbers, it goes to the sort of transformations that can happen in the universe. It goes to the most stable thing in the universe, and suddenly it matters quite a bit. So with the wrong combination of especially masses for the up and down quark, you can have it so that the most stable thing you can make out of up and down quarks it won't do what the proton and the neutron do, which is stick together and form nuclei, form the periodic table, form the basis of chemistry, form the basis of life, right? So you make a fundamental particle which won't stick to itself. So it won't, there's only one type of them instead of two, proton and neutron. There's one type of thing, and it won't stick to itself. So you have basically a periodic table with one element in it. And depending on how you mess things up, it either has the chemistry of hydrogen or the chemistry of helium, which is to say, if it's the chemistry of hydrogen, there's only one reaction in the universe. You can make a hydrogen molecule. And if it has the chemistry of helium, it has no reactions. It does nothing whatsoever. So suddenly from all the complexity of, I've got protons and neutrons, I can make carbon and sulfur and hydrogen and helium and gold and all of the periodic table, and I can put those together into all the incredible array of chemicals you see around you, with the wrong set of masses to the fundamental particles. Suddenly you've got none of that at all. You've got a universe with only one type of chemical element in it, and a chemical element that won't itself do very much. So that's the sort of example you get from fine tuning. You'll notice it's not that we can calculate whether there's going to be life or not. It's that we've found a system which is so simple that we sort of know everything that it can do. So if the universe only contains one type of particle which won't stick to itself and has the chemistry of helium, well, we understand the chemistry of helium. It's nothing. It literally doesn't do anything. And so there's no chance of it doing anything complex, let alone life. So that's actually one of my favorite examples. Very, very briefly for the other ones, how the stuff interacts, so forces. So, for example, there's the strong nuclear force. So it's responsible for protons sticking to neutrons. So obviously, if you want to make something in the universe, you better be able to stick stuff together. This is like having your Lego blocks actually connect to each other, right? At the most fundamental level, like this bit goes in that bit. If that fails, you're in real trouble. So wherever it is, if you knock it down to, I think it's about half of its value in our universe, anything big, carbon-sized or bigger in the periodic table. So carbon's only the sixth element. So you have 92 naturally occurring elements. You've erased, all but 5 of them, and 5 of the most boring ones, to be honest. The first 5 don't do very much chemistry-wise. Carbon's the real hero of the periodic table. So if you haven't got that force right, you just don't stick things together well. And finally, in terms of where stuff is, there's various ways that you need to start a universe off in for it to make any sort of complexity at all. You need an interesting one for me. There's a number that represents in the early universe sort of how lumpy things are, because it's almost perfectly smooth if you go back to the first, actually even as early as the first couple of 100,000 years after the Big Bang. We can see that in the cosmic microwave background. So if you go around to different bits of the universe and look at how dense it is, how much matter do you get per cubic meter here and there and everywhere around the universe, you find it's remarkably smooth, and the biggest change you get from place to place would be sort of 1 part in 10 to the power of 5. So, if I measure how much mass there is here and how much there is there, the first 5 digits will pretty much always agree, and there'll be just minor changes on those levels. So that's a way of characterizing how lumpy the universe is from place to place. And if you don't get that right, you create a whole bunch of problems for later on in the universe. If it's less lumpy than that, the universe will struggle to make any structure at all, because it's those lumps collapsing under their own gravity that form galaxies, stars, planets, all that sort of stuff. Very helpful. If it's too lumpy, then you're in danger of making not stars and galaxies and planets, but too many black holes. And you make structures that are sort of too dense. So once you've made a star and a planetary system around it, you want it to sort of be left alone for a while just to do its thing. And so actually there's been some interesting work recently trying to refine those limits. They aren't quite as tight as we thought they were, perhaps, but it's still an interesting constraint you've got to have on the early universe, that you just need this right amount of lumpiness so you don't get either a completely bland, boring soup of a universe, or just black holes all over the place.
Those are some pretty dramatic changes to the universe. If all we have is helium, or maybe we throw in hydrogen, or all we have is black holes, these are extremely dramatic changes. If I could have the audacity to suggest a different metaphor from the Lego ones, it feels more like stacking toothpicks end to end. And, every toothpick has to be perfectly positioned on a perfectly, flat surface. And then we're going to somehow balance a toothpick on top of that one and just keep going up. And if you have any toothpick out of alignment, or the end of it isn't perfect, you're not going to be able to build more than, 1 or 2 toothpicks up. I mean, just to get a single toothpick to rest on a table standing straight up is quite hard to do. And it sounds like what your book is saying is the universe is stacked light years of toothpicks up. And it's remarkable to see all the toothpicks in a straight line for millions of light years, that all of these things are aligned just the way they need to be.
Yeah. So that you've got to keep a separation in your head. So there's a way that analogy could be misunderstood. There's a way there's fine tuning could be misunderstood. Once you get the constants right, the universe is actually quite robust. You got to get a bunch of numbers right, and if that's the analogy for getting that's fine, that's good, that's exactly what we're talking about. But it's not like within our universe there's we nearly didn't make galaxies or something. If you get the numbers right, it's all right. The laws of nature will do their thing because they're the laws of nature. It's these other possibilities. It's these sort of counterfactual, as they're called, possibilities for these other values of these constants that that seem like a whole bunch of toothpicks just put on top of one another. I don't want people to think that. I gave a talk on this once, and a kid was quite worried that the universe was going to fall apart. It's like, no, ours is fine. Don't worry about our universe. Our universe is not a stack of toothpicks. That's the sort of work you've got to do to get the universe right in the first place. But ours has nailed it. Don't worry.
Okay, yeah. So no need to fear that one toothpick might get knocked off and it all collapses. Yeah. All right. So peace of mind for everyone watching. So let's talk about some of these free parameters. You mentioned the mass of particles, the strength of the 4 fundamental forces, the orderliness of the universe, the specificity of the cosmological constant, how inflation and the Big Bang had to be just right to deal with the horizon, the flatness, and the structure problems, the right mix of stable elements, the amount of low entropy at the start of the universe. And after each of these discussions, the two of you calculate out of the range of possible values that these could have been, that these ones are, very, very small probabilities in the whole space of potential numbers. And I was wondering, have you ever kind of added up all the probabilities at once and said, in light of all of these constants, here's how fine-tuned our universe is?
Yes, I have. So I've got a paper out, which you can find around the internet, published in a philosophy journal, called A Reasonable Little Question, where I try to do that. And I think you've got to be very, very careful about the assumptions you're making in terms of probabilities and what you think a probability is. You've got to sort of dive into all that sort of detail, I think, before you start messing around with that. The number you get at the end of it is remarkably small. I think it's 1 part in 10 to the number is 1 part in 10 to the power of, and then you got something, an enormous number down the bottom there. 136 is the number I end up with, which is just an insanely large number, or small number, depending on how you think of it. But you've got, I don't want to throw those numbers around just sort of as if they don't so much come directly out of the physics, so to speak. You've got to do a little bit of groundwork there, laying down exactly the question you're trying to answer and why you think you can answer it with probability theory. In particular, I think you need to... There's different approaches to probabilities, which we can get into the deep weeds here if we really want to. I think you've got to be very careful about the sort of question you're asking and why it is you think that you can talk about probabilities at all when you're talking about, not even our universe, you're talking about other universes. I think there is a possible sort of degree of fine-tuning, and I would put that number at, as ludicrously small. That, one chance in a number then with 137 digits in it.
So even if you were off by a factor of 5, we'd still be in a pretty challenging position there. Even the particulars of some of these, just they in themselves are so unlikely that just one of these variables that already has been investigated raises, the question, gosh, how could it be this fine-tuned, right? So this is just adding to the problem. So I want to ask about a different kind of question here. In A Fortunate Universe, you also raise the fine-tuning of biology. And you write, unfortunately, we have only clues as to the sequence of events by which life formed on Earth. This is an extraordinarily difficult scientific problem for 3 reasons. Firstly, life, even a single simple cell, is a miracle of complexity. Every cell in your body, for example, has molecular machines for moving itself, tagging and transporting molecules, processing food, defending against invaders, DNA duplication and repair, producing proteins, and receiving and processing outside signals. On top of all that, the entire machine can tear itself in half and produce a complete working copy in about 20 minutes. A modern computer is pretty great, but it can't do that. And so I know this is outside of your particular field of specialty, but what do you think of the case for fine-tuning from biology?
The way I'd think about it is, it's a big topic. This is a short story. So, if there's a pathway... So, one of the things that... The reason why I can talk about fine-tuning for life as a physicist is that what I can really do is focus on very, very broad requirements that life needs. Like, the stuff in the universe sticks together. Or, really, really basic stuff. Because I can get a handle on that. And the way we do it is not so much that... this is a common misconception of fine-tuning. It's not that we start with the laws and we predict everything that's going to happen in the universe. And, people say, we can't take the current deepest laws of the universe and predict that, a flower would exist from the bottom up. But we know that the complexity is there, that it sort of could happen. So people ask, well, how do you know with these other laws that what would or wouldn't happen? And the answer is, on very, very general grounds. We know that stuff won't stick to each other. If we were better at this, right? If we had a deeper understanding of the way that the fundamental laws connect with life and the processes by which life was created, we could put more refined limits on fine-tuning. we could really start to hone down. So, here's this sort of set of possibilities. And as a physicist, all I can do is with a very broad stroke of the brush go, not any of those ones. They're all boring. And, broad stroke here and there. And then over in this corner, we're like, okay, there's something complex going on here. We'll say that bit is at least life is possible there. It turns out that the life is possible bit is extraordinarily tiny compared to the total. But if we could really dig into the details and get a theory of how life could emerge naturally by purely natural processes, then if we understood that and we could get down to a fundamental level, connecting it to the fundamental level, we could really start to put some very, very refined limits on fundamental processes, initial conditions of the universe, to get not just atoms that stick to each other, but can we actually find where the sort of processes that might actually make life naturally, where they would turn up, what they would require from fundamental physics. So there are people who try to run the sort of, the argument from design from the fact that the origin of life seems extremely unlikely. And for me, it's not entirely clear when they do that, whether there's a question of whether you're doing the design argument like the fine-tuning argument's doing it, which is, do you think that when we have the natural explanation for all the things that can be naturally explained, will that explanation itself be kind of amazing? Which I think fine-tuning shows that it is. Versus, what's basically an argument from miracles. Can we find things in the universe that couldn't have been produced by the natural causes around us? For me, the origin of life, it seems like when a lot of people try to make that argument, they're really arguing for a miracle. And feel free if you want to do it that way. For me, I don't think we know enough to know whether there could be a natural process that does it that way or not. And, go and talk to all the sort of, Steve Meyer and that bunch, and they'll give you a very, very interesting and powerful argument based on information and all those sorts of things that you really should think very hard about. For me, even if we found a natural way that life could be formed, and let me just take a little sidebar here for a second, we should not be saying a naturalistic explanation for the origin of life, right? Because it's not naturalistic. It doesn't assume naturalism. It would just be natural. If I could walk into a lab tomorrow and go, hey, check this out, and just grabbed a bunch of chemicals, went pow, and made a cell, right? That would be a natural origin for life, but it wouldn't be naturalistic. It's entirely possible that God made a universe in which that's possible. I wouldn't be assuming that naturalism is true to say that these chemicals, bam, and I've made life. So it's a natural explanation, not a naturalistic one. But if there was a natural explanation for life, I think what that would open up is a sort of uber fine-tuning argument, where if we could really dig down at that level, we'd really start to, we wouldn't be sort of broad brushing it around parameter space in the fine, in the constants of nature. We could really dig down deep and see, oh, okay, I thought life could be here, but actually over there you can't have this process that we need for the origin of life, or that process, or this. So that's the way I'd think through it. I think if, given that we know that the laws have to be, and the constants of nature have to be remarkably fine-tuned to do such broad, blunt things as sticking things together, if you come out tomorrow with a process, a specific natural process, which turns the fundamental stuff of our universe into self-replicating life, I think you've handed me the ingredients for an uber fine-tuning argument to say, look, the limits that on the sort of universe that life needs, not just sticking atoms together need, will get even more fine, even more refined. So that's my broad, half-baked views on the origin of life argument.
We'll get back to physics here, but to try and sum that up, it seems that you're saying some people run this argument by saying, based on everything we know about all of the ingredients that are needed for a self-replicating living cell, that this is mathematically impossible to have a natural explanation. We're looking at a miracle here to get the origin of life. And you're saying, even if we find the natural explanation for the origin of life, that pathway is going to be so precise in terms of all of the ways a sun had to line up with a planet in the right orbit, with the right rotation, and a moon, and the right, temperature, and the right kinds of materials on that planet, and all the other factors that might go into, hey, here's all this, the exact scenario that would lead to the natural origin of life from non-life. All the factors that go into that would still give you a very powerful fine-tuning argument.
Yeah, that's basically it. A lot of the arguments from design, like, I get it. You just sort of, people say the universe has happened by chance, and then you go and actually look at something in the universe and go, come on, no way. Right? That's a powerful argument, don't get me wrong. I'm just hesitant to say that, it seemed to me it would be odd for a creator, a wise creator, to have made a universe capable of such complexity, but not quite have made it just, not quite have polished it off enough. He's still got to stick his finger in and make a cell at some point, and then off life goes. That's a theological and a pretty half-baked theological argument rather than a physical one.
Well, I think, again, I think some listeners, and at least myself, hear that and see it as an invitation to curiosity and to consider what natural means there could be for the origin of life. So another question I had for you is, in A Fortunate Universe, you state, we have so far emphasized that ultimately we don't know why things are the way they are. At the cutting edge of science, countless crazy theories float freely, unhindered by experimental evidence. The confusion swirling around cosmology, in which we don't know the identity of 95% of the universe, means that the time is ripe for a dramatic shift. And so I'm curious, like the Webb telescope is up and running. It's sending out all of this data. I imagine that's exciting to you and to others. Part of the whole point of that project is to overturn some scientific theories, right? That, oh, look, now we see this and that has to change that. And given that there's so much more to learn about the universe, do you think it's better to say, it looks fine-tuned. We understand, the masses of, the up quark and the down quark can't change, or we lose the periodic table. But, we still don't know what dark energy is. We don't know what dark matter is. We don't know how string theory might help us explain this. There's so much to be discovered. Saying we know it's fine-tuned, that's premature. What's your take on that?
Yeah, so I think the first thing to say is the point of the fine-tuning argument is very much to say take stock of where we are. Like, we have some remarkably successful theories that explain an awful lot about the universe. What's been called the standard model of cosmology and the standard model of particle physics. If you're thinking about the question, this is the sort of case I lay out in that A Reasonable Little Question article. If you're thinking about the question, this universe, is it sort of a typical, any old universe? Is this the sort of stuff that would turn up anywhere? As some very prominent atheists have been saying for at least a century, you think of quotes from Bertrand Russell saying, we're accidental collocations of atoms and stuff like that. Or is there anything sort of remarkable or unique or, rare or, untypical about the universe we see around us? Well, one way we can answer that is to say, well, what if we change, what other ways could the universe have been? Mm-hmm. So one way to explore that, which is a very useful sort of methodology for that question, is to say, all right, well, let's not just sit down with our imaginations and see what we can, think up. Let's take the fundamental laws, the best laws we have, the standard model of cosmology, standard model of particle physics, and try to change them in some way And a very practical, very rigorous, very systematic way we can do that is to take these constants and change these numbers and see what happens. And the nice thing about this is, if anything, it's biased towards finding universes like ours. Because what we didn't do was just go searching for any way a universe could be. We started with our universe and our laws, and then just sort of branched out from there a bit with these other constants. So if anything, it's biased towards finding universes like ours. But in fact, we find that most universes aren't like ours in that they don't support complexity. So that's the methodology. It's very much, look, we've got this question about the universe, whether it is something remarkable and rare, or whether it's just any old universe. And we've got a pretty good method for attacking that question systematically, with the best that science has at the moment. As part of that, by admission, you're not, if the best science we have of the universe changes tomorrow, we'll do it all over again. Right? We'll try to incorporate that. But as you said before, because we've got all these separate cases of fine tuning, all the different constants, masses of the particles, strength of the forces, the way the universe started off. I think that's not true is that some people say, the advances of science will automatically get rid of fine tuning. And that's not true, because what the scientific theories are trying to do is to describe the way our universe works. A scientific problem, at that level is a mismatch between what our theory says the universe should be like and what the observational data says the universe is actually like. And if they're not agreeing with each other, obviously, the universe wins. We need to go change our theories. Fine-tuning is not that sort of problem. It's a sort of deeper problem. It's our universe suddenly appearing to be very rare and having, unusual abilities against other ways the universe could have been. So there's no mismatch with observations so much. It's something where our theory is sort of not sitting, comfortably with itself, rather than not sitting comfortably with data. So it's not the case that the advance of science will automatically and necessarily get rid of fine-tuning. So I think the answer to that question is look, if you understand the method that's going on here, if you've got some better science, come at it. But for the moment, the best handle we have on this is the best science we have. It's doing a pretty remarkable job of explaining the universe around us. Not perfectly. There's loads of mysteries left over. Thank goodness. I still have a job.
So a couple of things I hear there. One is, it sounds, this kind of objection sounds like a pro-science argument. Like, hey, I don't want to tie my hands down and say it's fine-tuned. I'm open-minded to maybe it's not. But I think your rejoinder is, the science is pretty good. I mean, it's called the Standard Model for a reason. There's, international teams of researchers who find that these theories, they do describe the observational data remarkably well. And so it's kind of actually a weird rejection of the scientific consensus to say, I don't see fine tuning here. I just want to see what else, we discover. Is that hearing you right?
Yeah, I think that's about right. The progress. If you're saying, I'll wait for the progress of science. It's not. There's no guarantee at all. The progress of science, like I said before, with I would expect if there's advances in science, in sort of how life was formed, that's going to set up even more fine tuning in the fundamental laws, right? That's so the advance of science is going to. There's no guarantee it goes one way or the other for fine tuning. And so, what you're saying, I'll just keep an open mind here, is really saying I really hope the next advances in science completely overturn what we already know. And once you see it as that sort of objection, it doesn't make a whole lot of. It's sort of a pretty blind hope, actually.
Yeah. And the other factor you brought up is we started with success. This universe is killing it. We've got life.
Yeah.
And so we started with, the bullseye of all bullseyes. And then we said, how big is the bullseye? And it
Yeah.
turned out every direction you tried to make the bullseye larger, you found out once you did the calculations and the observations, this bullseye is extremely tiny. And that was why fine tuning is now widely accepted, is because that you started with success and then realized how unlikely success was.
Yeah. Although there's a couple of this is me talking to a bunch of audiences, knowing every little nitpick that people are going to make. So,
Yeah.
first thing to say is people sometimes ask, are there ways of making a universe which has more life in it than our universe? If you change here's there's a bullseye there, and where we know our spot is inside, but are there places where you could make more life than ours? The answer is we don't quite know, and the reason is because of that. This methodology is so broad. It's these broad brushstrokes that there's not really an obvious way you could do it. One of the ways which has been suggested in the literature is if you could make a universe with slightly more structure in it if you change some cosmological parameters. But even that's not entirely clear, because if you make a universe that's more dense, well, there's some stuff out there in the universe that you don't want to be too close to. There's big stars blow up at the end of their lives. There's things called gamma ray bursts, quasar. It seems useful to have a really big universe. Like I said before, once you've made a star with a planet around it, as far as life's concerned, let's just leave that thing alone. Like, we don't want too much else happening. So there's no particularly clear cases, but of can we make a universe which is better for life than ours? The answer is we don't really know, just because, again, it's not like we can take the fundamental laws and predict everything all the way up to trees.
Right.
Fine-tuning relies on this very simplified, here's another set of laws. Oh, I can't even stick stuff together. That's not a life-moving universe. That's as far as we can get. The other thing people will say is, well, obviously this universe isn't fine-tuned because so much of it is hostile to life. And that's just the wrong comparison. What that's comparing is our bit of the universe with other bits of the same universe. Whereas we're trying to work out whether our universe is sort of, fundamentally, rare or talented or something on a fundamental level. So we're trying to compare our universe with other ways the universe could have been. So comparing, we discuss this in the book, but as I said, there are reasons for the empty space around us. The Earth, it's great that there's not, breathable air out there in space, because we've got breathable air down here, but the Earth doesn't have to try and travel through air as it goes around the sun. Right? If the solar system was full of air, the Earth would just spiral into the sun in about a month. If I did that calculation right, which I'm not sure I did. As I said, you want space because there's stuff out there which is useful for life. Supernovae distribute the elements around the universe. You're made of stuff that was both made in and distributed by supernovae. So we they're great. You just don't want them nearby. So, there is a way that there's a logic to the way this universe fits together that includes all the empty spaces where, sure, if you were transported out there now, you'd be dead in about a minute. But, you're not going to be transported out there now. The gravity's pretty effectively sticking you down here, whereas, air and water and, donuts and stuff.
Thank goodness for gravity and donuts. Yeah, so we might wish to live in a Star Wars or Star Trek universe that's just teeming with life, but part of the specificity of the fine-tuning is the empty space is part of what protects life forming on this planet. So one of the most remarkable kinds of fine-tuning that you mentioned in the book was the one Robert Penrose finds. And you explain Penrose gives a rough calculation for every observer who observes a smooth, orderly, observable universe as big as ours. There are 10 to the power of 10 to the 123rd who observe a smooth, orderly universe that is just 10 times smaller. That's a number too large to even pretend to comprehend. And so what your argument here is about how, given that calculation, most observers in the inflationary multiverse will be Boltzmann brains. And Boltzmann brains are a really fun name, and I didn't want to leave them out of our conversation. So if you would bring that home for people watching, what's a Boltzmann brain, and how does Penrose's argument mean that we should expect those?
Okay, Boltzmann brains. This is where a lot of people get lost. When you're a cosmologist, you're, as a scientist, I'm a theorist. So the idea is I want to produce a mathematical model of something that captures the important pieces. So one of the examples we use actually in our later book, which is over that shoulder, Cosmic Revolutionaries Handbook, is imagine you've got a house and you've got a scale model of the house that just fits on your table. One of the reasons why you might make a scale model is you could use the model to answer questions about the house. So you've got your eye on this lovely new sofa or whatever it is, and you want to know, is that going to fit in the living room? And if you make a model of the sofa and you put it in the model of the house, if the model sofa fits in the model house, then if everything's accurate, the real sofa will fit in the real house, but that's a much easier experiment to do. That's a sort of microcosm of what we want a model to do, right? We want to be able to capture, enough about the processes happening in the real world that we can ask the mathematical model a question and get the same answer that we would get out of asking the real universe a question. As a cosmologist, the thing I'm trying to model is the universe. Now, the weird thing about that is I'm in the universe, and that's an odd situation to be in, right? Because usually if I'm modeling whatever it is, a tree or whatever, it's over there, or some particle experiment on my lab, it's over there, and I'm just looking at it. Whereas if you're modeling the universe, you're in a very weird situation that you're modeling the thing that sort of made you in the first place. And so you're not just a disinterested observer, you're in the system. So you've got to answer at some point the question, because it's crucial to all sorts of selection effects. Actually, So another principle in science is you not only think about what you're looking at, but what you're looking with. So what we see out there in the universe depends not only on what we're looking at, but what we're looking with, the sort of telescope we're using. So the classic example, is what wavelengths of light is your telescope actually going to see? The same that our eyes see, or radio waves, or something else. So if you're thinking about this in the context of cosmology, you do have to worry about, okay, where is life going to turn up in this model universe that I've made? Where am I likely to turn up? And if you think you've got a model of the universe, you need to think about where your observers are likely to be in that universe, because you're modeling a system where you're on the inside, so you have to worry about where the observers are. And so part of using that model to predict the universe where it is, to try to explain it, is, if there was an observer in this model, where would they turn up? Where would they be? And what you hope that the answer is, they'll probably be on a planet around a star, just doing what biology has done for, the history of life on Earth. However, you have to worry about that there could be other ways of making observers, right? Because it matters where the observers turn up, right? And in particular, if there's a way of making observers which is vastly different to the way we think we exist as observers, like on a planet, a long period of biology on this planet before we got here, if there's a different way of doing it, then that could be a real problem, because it would predict that most of the observers are that other kind of way of being an observer and not our kind of way of being an observer. So one of the ways that that could happen is if you have a sort of random process that is able to make an observer a short-lived observer purely out of sort of almost empty space, just particles hanging around. By chance, every now and then they come together with enough complexity to make, say, a brain that lasts for 10 minutes or something and then dissolves back into the background. Now, that seems ridiculously unlikely, which is why like, why the heck are we even talking about this? But if you find that in your idea about the universe, that type of observer is actually more likely than this type of observer, biology type of observers, then you've got yourself a problem, right? It's not a problem in reality. It's a problem in your model, right? Your model has done something, like something's gone wrong. You took a left turn at Albuquerque.
When your model's predicting brains coming out of nowhere and believing they're
Yeah.
you and me, that's
Yeah.
a falsification of your model.
Yeah, and now you might think that's really unlikely, but it turns out that some ideas that these Boltzmann, that's called a Boltzmann brain. The reason it's called a Boltzmann brain is that it was sort of originally found in an idea about the universe, which didn't sound that unlikely, from Ludwig Boltzmann. Boltzmann was a sort of pioneer of statistical physics in the early part of the 20th century, late 19th century as well. And so here was his idea. So the question is, why do we see a universe which has lots of useful energy around to use? Low entropy is the technical term. And his thought was, well, look, maybe the universe as a whole is in thermal equilibrium. Maybe everything's just uniform and boring and the same everywhere, and doesn't do very much. But by chance, right, all of the stuff will come together to produce a universe like ours. And you could only have life in a universe like that. And so most of the universe, most of the time, is dead. But the only bits of the universe that are like, oh, why do I have this sort of universe, are the ones where there was this random chance event that made a universe. Now, the reason why that hits the Boltzmann brain problem is because if you're sticking stuff together at random, right, the bigger, the more chancy the thing you're trying to make is, the less likely it's going to be to happen. So if you're waiting for an entire universe to happen that way, in order to then have inside of that a star, which makes a planet, which makes biology type observers, it's much more likely, that's an incredibly unlikely process, but it's much more likely to make the brain. The brain is more likely because it's smaller. You just need a smaller miracle. And this was pointed out in the 1930s by Arthur Eddington. And so there's, if you're doing cosmology, there's this worry that if you just think, oh, I know, I've got some unlikely scenario that I need to explain, maybe I'll just throw chance at it, time and chance and long ages, and that's all I need to do. Well, there's a way that can backfire on you, right? I mean, it is true that, if you, in Boltzmann's idea, if you waited long enough, this universe would turn up. Right. But all those other Boltzmann brains are going to turn up first in vast numbers. The way this works in terms of the fine-tuning argument is, there's a question of why we got just the right set of constants, why we got all these numbers right. And as an explanation that sounds a bit like what I just said before, maybe out there's a whole bunch of other universes, and you sort of pick your universe at random, and each universe picks its own constants at random, basically. There'll be some sort of physics behind the scenes for how to do this, like a random universe generator. And most universes are dead because they don't get the right constants, but anywhere where the right constants turn up, there'll be people like us, maybe not like us, there'll be some sort of life form going. Anywhere there is a life form, they must look around the universe and go, wow, we got a really rare set of constants. And so the worry is, if you're doing cosmology and you think you can solve a problem by throwing time and chance at it, you've got to worry about all the other ways to make observers. And so for these multiverse models, they have to worry about, and worry very seriously about, what's more likely for an observer? Is it more likely that they'll be like us, right? In a great big, finely tuned universe that's all doing beautifully and holds on to life and lets it develop over biological timescales and all that sort of stuff? Or is it more likely that you'll be in a freak observer in a non-fine-tuned universe, that you'll just be some freakish brain that came together for 10 seconds in a universe that doesn't support life in any sort of general overall sense? So, yeah, that's a long explanation of a very it's a weird idea, but it's absolutely necessary. If you're doing cosmology, you've got to worry about where the observer is because you're inside the system. And if you want to do something in cosmology, solve a problem by throwing time and chance at it, you've got to worry that the most likely way to make an observer in your idea could be these freak brains that turn up out of nowhere.
Yeah, it's a critical, and it is a funny phrase, and it takes some imaginative work to think this through. But to me, the fine tuning is so absurdly precise that if we need to multiply chances to get this to happen by randomness through a multiverse, then one reason to think the multiverse model fails is because it would be far, 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 far more likely that I'm a Boltzmann brain and all of my perception and memory and experience is a random occurrence in a universe hostile to life than to think that I am the person I believe I am.
Yeah.
And so this way of looking at, we're trying to evaluate the multiverse, right? And we're trying to do so rigorously. And this way of thinking about the model, I think, kind of shows that at its current stage of development, it's not a likely contender for explaining the fine-tuning.
Go into this in more detail in that paper I keep mentioning, a reasonable little question. At the moment, as far as I can, try to read the literature and stuff, the problem is that it's not so much that there are these Boltzmann brain problems. It's a problem that a fully fledged multiverse theory should have to worry about. But at the moment, I see in the literature sort of that models that you can't even make predictions out of. They're sort of toy models, proof of concept sort of ideas, but sort of almost too, they don't quite have the sort of intestinal fortitude, the sort of the rigorousness down at the base level to make predictions in any sort of coherent and convincing way.
The last question I want to ask you is, you say that the fine-tuning points to God and that our universe points to God, that the order we observe in this universe, that's best explained by a personal agency. And so I'd be curious to hear directly from you why it is you think the fine-tuning points us in the direction of God.
If we're thinking about that question of is there anything remarkable, anything rare, anything special about our universe, I think the fine-tuning is the best way to get a handle on that. And the answer is sort of overwhelmingly, yeah. This is not just any old universe. I mean, even on the most broad, like, our universe sticks stuff together, right? That's an amazingly rare talent, it turns out. Okay, so what do we do with that? The worry I have about the multiverse is that it's not necessarily the case that advances in physics, even the multiverse, will reduce the degree of fine-tuning. Right, it might turn out to be a very rarely talented multiverse that makes more life like us than Boltzmann brains. So if you're looking at explanation for that, you either take that as it is, and just, if you're a naturalist, then the universe just is all there is, and that's all there is to it. And that should be a very uncomfortable fact for you, because, it's... and you see this in the way that naturalists almost instinctively try to play down anything that looks remotely special about the way our universe is. They if they're not extolling the beauties and wonders of science and how amazing the universe is, then they sort of catch a glimpse of, oh, wait a minute, we better play things down a little bit. Right, we're just a third rock around an average star in the outer bits of some boring old galaxy, as if these are perfectly ordinary things. If that approach doesn't quite satisfy you, if you'd sort of thought that, when science is done, all the mysteries of the universe will be solved and everything will be explained, and suddenly you see this fine-tuning thing, which is the sort of thing that won't necessarily be explained, even if we had the ultimate laws of nature. The question is, what sort of other type of explanation is out there? And we see in fine-tuning something weird about the universe, that it seems like the sort of explanations are kind of backwards, that the way the universe turns out is a deciding factor in the way it started off, right? As if, so there's a great quote from Freeman Dyson, who was a Nobel Prize-winning physicist, just saying that it seems like, the laws of nature knew we were coming. That the way the universe turned out has, in some sense, I was going to say decided, but that's too influenced, or in some way the way the universe has turned out has set, amongst all the possibilities the way the universe could have been, has influenced the way that our universe turned out. And if you're taking that idea seriously, I mean, you're almost directly talking about a mind. That's why it's so hard not to say decided, right? The sort of thing that can look at a bunch of possibilities, see the way it's going to turn out, and then choose that one from the start. That's something a mind does. That might as well be just the definition of intentionality, or being an agent, or being mindful, able to make a plan, able to have a purpose. That, I think, is a very natural sort of progression from our universe looks like, when it was a fraction of a second old and just full of, this seemingly random assortment of particles, and various other things, and just a certain level of lumpiness and this, that, and the other, that someone knew that was the right batch of stuff to make a universe which later on was going to make, stars and planets and life. So I think that's the way I'd lay out the way you get from fine tuning to an explanation of fine tuning that takes it seriously has to take into account the fact that it looks for all the world like the universe knew we were coming.
And that's it, because the idea of the universe knew we were coming, when you examine it, is kind of a nonsensical phrase.
Yeah.
But a mind knew we were coming.
Yeah.
That makes sense. And so we have the scientific evidence and we have the logical inference. And I think it comes down to really what we want to be true at some level. Because it does seem to me that everything's pointing in the direction of intentionality, purpose, ordering, design. Those are the kinds of that's the work of agency that would result in the kinds of those things as we've observed them in today's conversation, and that's a reflection of the scientific work. And so it all fits together. The question is whether or not we're open to that conclusion in some ways.
Yeah. So one of the issues I've found is that this idea of God as sort of a bloke up in the sky with a big beard and all that sort of things. But from, a most basic thing of, a mind that can make a plan before it implements an action, and that are capable of seeing what the outcome of this universe would be before putting it into, action. That because of fine-tuning, that sort of explanation does a lot of work for explaining why our universe is the way it is.
Well, thank you, Dr. Barnes, for writing these books, and I will put links to them and to the paper you've mentioned in the description for this video so people can easily click over and get those and access that literature. I found my mind was expanded from the conversation, gave me a lot to think about, and I hope anyone who reads it will simply find more enjoyment in the scientific process and more fascination in all of the wacky parts of the universe we live in. And if they have a good sense of humor, they might get a few laughs out of the book as well. And so thank you so much for writing them and for being on today to share with us. But if you really want to integrate this into what you understand about reality and be able to talk about it with others, what you need to do is what I did, not just read the book, but write down your thoughts on the book and actively process that information. And if you'd like to come do that with me and others in the Uncommon Pursuit community, I think you'll find that by writing down your thoughts on this conversation, just the process of articulating it in a written format is going to force you from confusion to clarity. And it's going to enable you to take this conversation forward with your family and your friends and your neighbors, and to make sure you have an accurate understanding of the material. So let me invite you to go to uncommonpursuit.net, create a free account, and jump in on the conversation about this interview. Also, hope you'll join us for a future event. Dr. Barnes, again, thank you for your time and your expertise, and really been a pleasure to interact with you today.
Thanks for having me.